So as introduced, I'm going to be speaking today on behalf of myself and Paola. We decided because of the virtual venue that I would just present rather than trying to hand this back and forth to keep things going smoothly. So I will be speaking today about why we're doing what we're doing, how research has been evolving, and where we're going with it. How our Cyberinfrastructure at the Pittsburgh Supercomputing Center has evolved, and where we're going in the future with that. I'll then give a few examples of the successes we've been seeing, and then go into a little more detail about what Bridges 2 will be, because this is really an exciting time. This is a great time to give this talk, and I hope that some of the people who are in the audience will be able to benefit from it. So to begin, the first question is, why are we doing the sort of things we're doing? The real issue is that the needs of artificial intelligence have been growing exponentially. I think a lot of the people in this audience realize that, but I don't think it's very widely known just how fast they're growing. In the Stanford AI Index that was published last December or so, one of the salient points that was made was that the compute needs of AI have been doubling every 3.4 months. That's radically faster than Moore's Law ever went. It's more than we will get by simple hardware advances, even though there's some really, really exciting things happening now. And so this is going to need a lot of work in algorithms, in doing things more cleverly. And so we've been designing systems that can help us do that. To make it more concrete in terms of complexity, slide 4 shows several examples. On the left are convolutional neural networks. So these are the networks we all know very well, things like ResNet and VGG. And looking at the number of computational operations in gigaflops on the horizontal axis, the accuracy they're obtaining on the vertical axis, and the number of hyperparameters represented by the size of the circle for each. And what we can really see is that the numbers of hyperparameters are getting very, very large in the large VGG networks. The number of operations per iteration is increasing. These are just trends that we're dealing with. And those are just the convolutional networks. On the right are transformer type networks. These are the ones that are very valuable for time series analysis, where you want to have long short-term memories, do machine translation, but also time series analysis in, for example, medical data. And what I think is really interesting here is the rate at which these networks are growing from hundreds of millions to billions of parameters. That has ramifications both for computational complexity and also for the amount of memory that is needed to represent them in the hardware. On top of that, we have additional sources of complexity. GANs, or generative adversarial networks, compete networks against each other. So this effectively increases the number of iterations that are needed. Domain adaptation is a similar idea. And reinforcement learning from first principles and building up from that, all of this adds iterations are effectively multipliers on top of the number of parameters and the overall space. And so what we're getting from this is really a need to blend HPC and AI. There have been a lot of great results that people have accomplished on their desktop systems with a great consumer class GPU. But what we're seeing now is we need to go beyond that. We need to scale to many GPUs together, novel hardware that will go orders of magnitude faster than that. What we've been building at Pittsburgh is really an ecosystem. We started, and those of you who were at my talk last year, it mainly focused on Bridges. So we start with Bridges. Bridges was really the first system in the world that really brought together high-performance computing, AI, and big data. We designed it in 2014. It went to production in 2016. And it has been growing. We made a bet with Bridges that we would be able to sustain this kind of an architecture where we really implemented high heterogeneity, a single parallel file system to make all data equally accessible from any modality, whether it was HPC, MPI codes for AI for deep learning, or big data with Spark and Hadoop. But be able to get all that data with a single spot, not have to move it, and to be able to develop these complex workflows that we actually need in science, engineering, medicine, and other fields to make research progress very productively. This ecosystem grew. The first thing we added to Bridges was a file system designed for the Pittsburgh biology community. We have a project called Big Data for Better Health. There's a new Center for AI Innovation in Medical Imaging, or CAIIMI, that's from the University of Pittsburgh Medical Center, UPMC, Pitt, and CMU. The point there was this community needed very stable file storage without writing proposals to get it, and they needed fine-grained access controls because a lot of this is dbGaP type protected human data. We then added the Brain Image Library. This is an NIH-funded collection of brain data. It's up to about 15 petabytes, another collaboration, and really enabling being able to do high-performance data analytics, potentially AI, across this unique in the world resource of big data, leveraging Bridges for the compute. We've added a number of campus clusters from the University of Pittsburgh, Carnegie Mellon, and a large NSF MRI cluster from West Virginia University. And the point here is really looking at this as a cloud, where the dedicated cluster for the department or the group or the university is their dedicated resource, but they can then essentially burst out to Bridges and its large file system in a cloud-like sense. In 2018, around July, we designed Bridges AI. And my co-presenter, Paola, really designed this, and we put that into production in January of 2019. I'll get into more detail about what that is shortly. But then we've also added to it the Human Biomolecular Atlas program, or HUBMAP. HUBMAP is an international consortium. Right now there are 19 lead institutions, over 50 institutions participating overall. And the first data release hasn't even happened yet. That's a hybrid on-prem and commercial cloud approach, which is leveraging Bridges and Bridges AI for some of its compute. And it adds its own storage. So where does this go? I mentioned that we had bet on Bridges as an architecture we can carry forward. What has happened since then, and what I could not announce last year at the Stanford conference, was Bridges 2. NSF awarded us with funding for Bridges 2. We will be building that this summer. And I'll get into more detail on that in the second half of the presentation. But essentially, Bridges 2 really builds on what we've developed. It builds on the track record we've established with bringing together HPC, AI, and data, but then adds some new components, makes everything, of course, bigger, faster, and really transformatively new. Bridges will run through November of 2020, this year. Bridges 2, we will be building this summer. There'll be about a 4 to 5 month period of transition, and then we will be moving things over from Bridges 1 to Bridges 2. And I expect most, if not all of them, to move across. So as a quick refresher, I'm going to go fast through Bridges 1. This is mainly for people who have not seen this. It's a fairly large system. It was a $10 million NSF acquisition, plus an additional supplement that provided Bridges AI, that Paola directs. It has about 30,000 Xeon cores, 88 Volta GPUs, DGX2, a number of HPE Apollo servers with 8 Voltas each, a lot of memory, up to 12 terabytes per node. Its whole point is, though, making a heterogeneous system available where different node types are optimized for different parts of the workload. And then on top of that, putting on very flexible, user-friendly software layers like Python, Anaconda, Jupyter Notebooks, R, MATLAB, and so on, to let non-experts use an HPC machine as if it was a desktop. Many of them actually come in through web interfaces. The architecture is here. We'll look again at this for bridges 2 because the idea carries through. The point here was a single fabric. This was Intel OmniPath, and everything interfaces over that. The compute nodes are in green on the bottom. They all have equal access to the parallel file system. That includes nodes that are provisioned for doing Spark or Hadoop. There are additional utility nodes on top, and then all of that interfaces to the U.S. national research infrastructure, including SEED, campuses, and large-scale instruments. The architecture is here. I've not yet done this diagram for Bridges 2. That's on my list after many, many deadlines this spring. But the point is, it's a novel interconnect. It's a fat tree close architecture. And it lets us really deploy a data-intensive solution with maximum cost effectivity and very, very high performance. And all of the node types in Bridges actually have a role in AI and high-performance data analytics in addition to serving high-performance computing. The way it makes all this accessible, which also carries through, is the heterogeneous node types, really blending CPUs and GPUs under one infrastructure. We prioritize interactivity, and this is just huge. People need to be able to debug and work with things in real time. Eventually, they may be happy with batch to get things running in production. But leading up to that, interactivity is critical. All the popular languages and frameworks that people use are very actively supported. And Paola's group actually supports all the deep learning frameworks through containers, especially the NVIDIA GPU cloud, containers, and others. We make available community data sets. And much of this ties into gateways through which many users, even up to tens of thousands, access the system remotely and without having any idea they're using a high-performance computer as a backend. I would say community data sets are critical to this. One thing we've been doing with this recently is standing some of these up for COVID-19 simulation modeling. So Paola has taken the lead on standing up the 2019 NCOV-R data set that's published by the Chinese National Genomics Data Center, updating that several times a week. And we also are willing to do others as people need them. The whole point here is that everyone should not have to bring their own data. And by standing up these very high-value common repositories in situ with high-performance infrastructure that is no-cost access for open research, this really democratizes being able to do scientific discovery based on big data. It makes things much easier to use and brings the cost effectively to zero. Very briefly, I just want to cover Bridges AI. This was the new addition we introduced January, just over a year ago. And it contains two kinds of servers. It also is heterogeneous. The point is that there is no one-size-fits-all. We have an NVIDIA DGX2 for the most demanding AI challenges. When we dropped it into Bridges AI, it was the most powerful AI server in the world, and it's still up there. It had 16 Tesla V100s or Voltas, 32 gigabytes of HBM2 memory each, and then the switch that couples them all at 2.4 terabytes per section bisection bandwidth. It has 30 terabytes of internal NVMe SSDs for very, very high data I/O. And it is just the best machine you can get to right now in the NSF ecosystem for doing scalable artificial intelligence. If you need to get on it, let me know, and we'll arrange access. Bridges AI also contains 9 HPE or Hewlett Packard Enterprise Apollo 6500 servers. Each of these have 8 Volta GPUs, basically half the power of a DGX2. But there's difference. There's difference in price for the box, and so this lets us really balance the maximum capability with the DGX2 with also really great capability, but also yet more capacity with 9 of the Apollo 6500s. Not everyone needs the DGX-2. If you need it, it's invaluable. If you don't need it, there's a lot more here. And people are using these as well for COVID-19 modeling now, specifically in drug discovery. Now, these are allocated through the NSF Exceed program as is bridges. And we also have staffing to help, especially if people have a problem that they have been running on, say, a desktop or a laptop, and they would like to know how to scale that to many GPUs to improve time to solution, get more iterations in, optimize the network, optimize hyperparameters, and do that very effectively. These support all of the containers you expect and all the AI frameworks, significantly from the NVIDIA GPU cloud, but also other native builds, things that people install on their own through Anaconda, and so on, as well as basic machine learning, like through NVIDIA's Rapids framework. I'd like to jump now to some ways that this has all proven successful. To give you an idea of why this scalable HPC and AI architecture has value, how it is different from what people can get in their own departmental resources or even in commercial clouds. And then a couple other very quick examples depending on how time goes. So the first one I'll cover is it's been an evolving story that has gone from fundamental research decades ago to national defense applications now. The story in these slides starts with a machine we call Blacklight in 2015. And Blacklight was the world's largest shared memory machine. It was an SGI UV, had 32 terabytes of cache-coherent shared memory in two 16-terabyte partitions. The point here is that the application was poker, and a specific kind called no-limit Texas Hold'em. This is important because poker is a stand-in for real-world decision-making where we don't have complete information. In poker, we don't know what the opponents have in their hands, but more importantly, we don't know what their strategy is. We don't know how they choose to bet, bluff, how they choose to raise, and they change that. Humans, of course, evolve their strategies, and so an AI has to do so as well. That makes this game fundamentally different than something like chess or Go, where the full state of the game is known at any instant. In those games, you look at the board and the pieces, and you know everything there is to know. In poker, you don't, because there's this strategy element. The game has 10 to the 161 situations, which puts it very close to the computational complexity of Go. And interestingly, the way Professor Sandholm refers to this is 10 to the 161. It would be the number of atoms in the universe if every atom were itself another universe. So it is a lot of complexity. This began even before that on other PSC systems and other smaller systems with poker bots called Tartanian. The CMU mascot is the Tartan, so these were Tartanians. Clodico came along in 2015. Clodico was cool because it basically tied the best human experts in the world. These are professionals who are very mathematical and very analytical. That was a tie. Okay, it's progress, but not what you want. Along came bridges. In 2017, the competition was done again. There were advances in algorithms. But the big difference was bridges was a supercomputer. It was an HPC machine. It had tightly coupled nodes with OmniPath. For this game, we needed that. We needed the HPC resource because each hand was being played by 50 nodes concurrently. It generated a 2.6 petabyte knowledge base. This could not have been done on other resources. It generated a great paper in Science at the top right. Fast forward to 2019, and we took it to the multiplayer scenario. I'd say in 2017, people said, this is great, but it was for heads-up Texas Hold'em, which means one player against another. Of course, the way people really play is 6-player or some other number. And that's much, much harder because now you're dealing with multiple players and there are multiple strategies. That happened this year. That was also a resounding win. The first competition in 2017 was a very high-profile event being followed on Twitch, and it was very much a real-time 20-day show. The one in 2019, because it's so competitive, was actually done quite quietly until it was successful. And it was successful. It was another great science paper, made the cover of Science. And significantly, the 2019 Marvin Minsky Award for Outstanding Achievement in AI, which I think of as basically the Nobel for AI because that is the highest award, was awarded to this team for what they had done in 2017. The selection committee had met before they even got to have their 2019 result, which was even more stunning. And the chair of the committee highlights why this is important. Poker is a game, but it's a stand-in for other things like economic negotiation, cybersecurity, and other things where we just don't know the full situation and where that situation is rapidly evolving. This led to the formation of two companies, Strategic Machine Inc. and Strategy Robot. And Strategy Robot, which is aimed at the defense sector, received a 2-year contract from the Pentagon to look into applications of these algorithms of interest to them. Strategic Machine Inc. is aimed at other applications in things like biotechnology, economics, and so on. So this is a really great example where fundamental algorithm work developed long, long ago has progressed to the state where the algorithms are surpassing human expertise and they're finding real-world applications. And what it required was HPC to make that happen. This also was one of the Science magazine's 10 runners-up for 2019 Breakthrough of the Year. Again, Science magazine is not a computer science publication, so this is a real breakthrough. And I applaud Professor Sandholm and Noam Brown for all they accomplished. I'd now like to transition for a few minutes into a deep dive into a medical application that has been enabled by AI. And it's specifically because it shows why we need scalable AI, why a desktop GPU is not enough. This is work that we wrote a paper on in the fall. Paola Buitrago was the lead author, and then Drs. Joel Saltz and Raj Gupta at Stony Brook Medicine, who are computational pathologists, who are really working on digital pathology and using Bridges AI to advance their research. This project was awarded the HPC Wire 2019 Award for Best Use of HPC in Life Sciences. And so I'd like to just tell you a little bit about what Dr. Saltz and Gupta have been doing, why this is important, why it matters to all of our health, and why we need scalable AI to make this work. So the key here is that this relies on what are called whole slide images. So these are microscope slides of biopsies. These are tissue segments. They're macroscopic. You can see these with the naked eye. They're big. They're slices of some organ that has a tumor. And because they're big, their resolution is extremely high, up to about 100,000 by 100,000 pixels, and 1 to 4 gigabytes each. That's radically different than the image sizes we have in benchmarks like ImageNet. This is why we need benchmarks specific to scientific applications, in addition to the other things being pursued in MLBench and industry efforts. A project that Paola leads called OpenCompass, and a complementary project called Compass aimed at the private sector, are looking at exactly that for emerging AI architectures. Namely, how do new architectures help, or not help, as the case may be, research problems in large-scale imaging, time series analysis, 3D volume analysis, or whatever is relevant to research. The project we're talking about here is in digital pathology, which is really looking at quantifying analysis based on these large-scale image data. The key here is looking at TILS, or tumor infiltrating lymphocytes. From grade school biology, remember that lymphocytes are white blood cells. These are the cells that go around and they kill bad stuff in our bodies. But they have to be activated. With COVID-19, we know that is about building immunity. The antibodies cause that to happen. In this case with tumors, we would like to know whether or not we can do precision immunotherapy by activating a patient's own immune system to wipe out the exact kind of tumor they have. It turns out that's very dependent on how widely spread these interstromal and stromal TILs are throughout that tumor sample. This is a very rapidly evolving field. There's a website I have on this slide that you can learn a lot more about it. The key here is that in the top left, we have a pathology image. The tumor has been segmented by an expert human pathologist. That's the red outline. The percentages of tumor intensity are in image B, and then the likelihood of TILs, these lymphocytes infiltrating that tumor, are in C, and then D is a combined map of the two. And what we'd really like to know is, are these TILs infiltrating the tumor such that they can be activated and kill it? Are they just clustered around the outer boundary, or are they not present at all? So this is a different application. We've seen a lot of applications in medicine where people just work to segment a tumor. Those have met with fairly good success, and they're very useful in pathology. This goes a step further. I'm not a pathologist. I could not begin to look at these images and reach the kind of conclusions the experts do. And the way they've done this is they actually train two different networks, one for cancer detection, one for lymphocyte classification. At the time, they evaluated VGG, ResNet, and Inception, and the reason is computational performance. Larger networks may, in fact, do better, but they're a lot more demanding, and even on Bridges AI, these are demanding runs. And we could use even more. There's a publication here that covers it very well. An interesting facet of this is that these convolutional networks were pre-trained on ImageNet, implemented in PyTorch, and then trained further on the medical images that are of interest. That pre-training on ImageNet, even though those images are completely irrelevant to this pathology, actually turns out to be a big advantage in training them faster. The training results are here. I'm not going to go through them in detail because of time, but we will make these slides available for you. And these numbers are straight from the papers. The bottom line is they're getting higher accuracy than had been previously reported in the literature on positives and negatives. And the same goes for the lymphocyte detection network. They're also improving the F1 score, the accuracy, the area under the curve. And these two networks then work together to give essentially the heat map of where the lymphocytes are in the tissue. Just to give you an idea of the complexity of what we're looking at and why I find this to be an impressive result as a non-pathologist, these just give you ideas of the kind of tissues these are examining. They're actually very different. Each row is from a different set of pathology images. You can see that the staining is somewhat different. These are what are called H&E stained. So the ratio of pink and purple are different. The structures are different. Very different topologies in the samples. And so to be able to cope with this from both the segmentation and the lymphocyte detection really shows fairly good generalizability. I'm going to jump ahead because there's a lot I want to get to. The one point I want to make before I move on, though, is that the initial samples and the initial studies were all done on breast cancer. This has since been extended to other kinds of cancers, like pancreatic, prostate, and others. And it also works there. So the transferability is also good. Bridges AI helps with this by really supplying very, very large-scale compute, scalably. It needs this for both training and, in these cases, for inference. So having these 8 and 16 volta systems where they can train a network and then do inferencing on that network in an extremely large memory computationally powerful server has been essential. I now have several other examples, and I'm going to go through these really quick because I'm down to 8 minutes. The first one is more medical imaging. This is a colleague of mine, Shandong Wu, who has started a Center for AI Innovation in Medical Imaging at the UPMC Hospital Complex and University of Pittsburgh. There's also a collaboration with Carnegie Mellon. And here he is looking at multimodality breast cancer imaging to really improve accuracy, to be able to reduce the number of false callbacks in patients, and give patients a much better outcome medically. Internally, we're doing work with student interns. The individuals in the title bar with asterisks are all undergraduates, and looking at doing 3D deep neural networks and interfacing that with spherical harmonics to look at tracing connectomes. This is doing a zebrafish larva. It's a great starting point. Of course, where we'd like to go is larger data sets, perhaps in the brain image library. We have other work that combines very large memory genome sequence assembly with deep learning. In this case, looking to identify antibiotic-resistant microbes relevant to agriculture and plants. This work is agriculture. Clearly, the same methods will also be applicable to COVID-19 research. It's extremely pressing right now. Of course, we have a lot of work in other fields and other sciences. It's work from Asad Khan and Elio Huerta at NCSA and University of Illinois, looking at classifying galaxy types. Again, running on Bridges AI for scalability, and the high-performance interconnect is essential for that. The Human Biomolecular Atlas I won't have time to go into today, other than to note this is a very large project. It is building a single-cell atlas of the human body for all major tissue types except the brain, because that's covered otherwise. We'll have our first data release for summer of 2020. Contact me if you'd like to learn more. And I would like to jump now to Bridges 2 and what it will be. We really designed Bridges 2 for rapidly evolving research. And what we mean by that is a combination of course, ongoing high performance and high throughput computing, high performance AI, and AI and enhanced simulation modeling through surrogate models and data analytics, the community data that we began Bridges 1 and are absolutely continuing, along with big data as a service, which is bundling software and analytic tools to be able to work with it in place by non-experts. Then, of course, carrying forward the familiar productive software environments and supporting very robust workflows including off to commercial clouds. So Bridges 1, I'm going to skip this largely because Bridges 2 is really moving to all of these things, bigger, faster versions. What we'll introduce is full system AI, much more powerful processors on each node for doing inferencing. It will introduce a fast flash array to accelerate deep learning as well as some genomics. It will have Mellanox HDR200 InfiniBand throughout, a new tiered data management from disk to tape for data resilience and archiving, and cloud interoperability. This is the classic one-slide summary of what Bridges 2 is. These are things we normally produce for the National Science Foundation, but works well for this very quick talk too. Like Bridges 1, it has a unifying interconnect that ties all the storage together. Everything with an asterisk here in this diagram is new or improved. So we have a new flash array, we have a new tape backup and archive. Those are maintained in a single namespace through HPE's Data Management Framework, or DMF, to make it very easy for users and staff to migrate things on a rules-based basis. Again, a lot of nodes, heterogeneous regular memory, large memory, extreme memory, and GPU nodes. One thing that is different here, aside from the HDR200 network, is the GPU nodes are all connected over multiple HDR200 links, 2 per server, to be able to scale deep learning across up to 12 of these HPE Apollo 6500s at very high performance across all 24 of them, with some reduction in bisection bandwidth, but still, given the topology of deep learning training, it will work really well for scaling out. There are a number of factors in Bridges 2 that really center on productivity, usability, and interoperability. Productivity is about being able to use multimodal data and serving non-traditional users, delivering community data sets and big data as a service, and the HPE DMF is going to be a big help for a lot of that. The whole system is an AI engine now. We have deep learning training nodes and deep learning inferencing across the whole thing. Usability is through all these very familiar frameworks. The same things we use in our laptops will work on Bridges 2 as they do on Bridges 1. And containers make that very easy to go between Bridges 2 and the commercial clouds, as we're doing for HUBMAP. Interoperability will be continuing and increased. AWS, we're already working with for HUBMAP. We expect to go to GCP as well, and there will be others added on. Some examples of what we're serving, I'm not going to go through in detail. We can take questions. I would just like to jump to the summary slide, though, since I'm in my last minute. And to say that AI is really a part of the workflows we're doing. People are analyzing big data. They are deploying surrogate models. They're speeding up simulations by many orders of magnitude. We've been seeing that. We've been seeing it speed up, for example, quantum chemistry by 5 or more orders of magnitude with no decrease in accuracy. And so we've been designing our systems to facilitate that. This is critical moving forward. Bridges 2 will extend the concepts we've proven. It will add new great things. We have our early user program planned for August this summer. If you'd like to be an early user, contact me and we'll get you on. Production is scheduled to begin in October. We are taking startup and education proposals at any time. I don't think that's set for Bridges 2 just yet. That will be very imminently. By any time, I mean those are always going to be accepted once it opens. That'll be soon. And then larger research proposals, it could be for very, very large amounts of research. Computing, those are reviewed quarterly. Next window for those is June 15th to July 15th. Again, if you'd like to talk about those, I'd be happy to do that. And all of this, most importantly, is absolutely free of cost for open research from US-based PIs. And we're really, Bridges 2, like everything we do, is all about inclusion and diversity and building collaboration. So we also welcome international collaborations. So with that, I will turn it over to, if we have time for a question or two.
Yes, thank you, Nick. We do have a couple questions. Let me just sort it out really quick here. So we do have one. Are you running multiple nodes training jobs with NGC and HPC scheduler?
So right now, I'm not aware of any users running multiple node NGC jobs. We've absolutely had users running multiple nodes on using Horovod with their own builds. I don't think that's with using NGC containers. Okay. I would be happy to check into that, though, and get back to whoever this is. If these questions are captured in the chat, I'll be happy to get back to people on those specifics.
Yes, yeah, they're captured in chat. The next question is, this may refer to the DGX, but why 8x ConnectX?
So why 8x ConnectX? That's simply because that is what the DGX2 is built for. In theory, one can run 8 times EDR InfiniBand between multiple DGX2 boxes and really achieve phenomenal scalability to do deep learning training across multiple boxes. We did not do that simply because of a budgetary constraint. It will be very interesting to do, and we do have great interest in scaling multiple high-performance AI-specific servers in ways that will actually be quite exciting. And there are projects we have in mind that I hope to be able to talk to you about in the future on that. But basically, yeah, the 8X that's built into the box. It is to make it an incredibly scalable AI box. We did not exploit that, but others can.
Okay, thank you, Nick. That was the last question.
Okay, thank you all. Look forward to the rest of the conference.